A function that returns another function looks strange the first time you meet it. The strangeness disappears the moment you accept one idea. The thing coming back is just a value. You can catch it in a variable, hold on to it, and call it later, exactly like catching the number 10. Here is the function we are working with. MakeProd takes a parameter. A defines an inner function g whose body returns A times B, and then returns g itself, the function object, not a call to it. Last time we ran it as a chain, MakeProd of 2 called immediately with 3 all on one line. Now the exact same computation written with an intermediate name. First line, doubler equals MakeProd of 2. Second line, val equals doubler of 3. Then print val. We save the first half of the chain in a variable and let that variable do the second call. It does exactly the same thing. Trace it. Running the program creates the global environment, the scope of the main program. Inside it, one function definition, the name MakeProd pointing at some code. We do not care what that code is yet because nothing has been called. Next line, we create the name doubler in the global environment, and it is going to equal something. That something is a function call, so a new environment is born. One new environment for every call. This is the scope of MakeProd. The definition says one formal parameter, A mapped to the actual parameter. So A holds 2. Now we execute the body, and the body creates a function definition named g, pointing at some code, same as before. Now the interesting part. MakeProd finishes its call by returning something, and the thing it returns is the name g. That name happens to point at a function object, but treat it like any other value. Compare these three lines. Doubler equals 10. Doubler equals a list of numbers. Doubler equals g. All three assign a value to doubler. In the first case, the value is an integer. In the second, a list. In the third, a piece of code associated with a function. The assignment mechanics never change. Only the kind of thing on the right-hand side changes. Assigning works whatever the value is. It is only the calling on the next line that needs doubler to hold a function. So out in the main program scope, doubler equals g. This is the memory picture from the aliasing rule. Writing my func equals is even with no parentheses, gives one function object two names. The same thing has happened here. Doubler is one name, g is the other, and both arrows land on the same function object in memory. Nothing was copied. There is still exactly one piece of code sitting in memory, and now two labels point at it. Two names for one object means we can use doubler on the next line. Doubler of 3 is exactly like g of 3. We are simply using the name we saved it under. It is a function call, so we create another environment. Call it the scope of g or of doubler. The name on the box does not matter. One formal parameter, b holding 3. The body says return a times b. b is 3 because you just called me with that value. But what is a? There is no a in this scope, so we do the same trick as before. We look outward to the scope where g was defined, the call to MakeProd, and grab the first a we find there. That scope has 1 holding 2. 2 times 3 is 6. That 6 returns to whoever called us out in the main program scope, so val holds 6 and the print writes 6. There is no particular reason to prefer this two-line version over the chain. Both build the same environments in the same order and both produce 6. In practice, you would usually reach for the chained form simply because it costs fewer lines of code. The intermediate name earns its place as a teaching aid. It makes the return function visible, sitting in a variable with a label, instead of vanishing into the middle of one dense line. With a little practice, the chained form becomes just as easy to read. Now the honest question learners ask, why bother? In this example, all we did was double a number. You could write that without returning a function at all. It looks like overkill, because it is. The example is deliberately trivial so that the mechanism is visible. You would never write a function returning a function to double a number. But for larger pieces of code, it is a genuine technique, and it buys you three specific things. The first is scoping. In a large project, if every function you might ever want lives at the top level of the main program, the top level becomes a mess. Sometimes you want a helper to be visible only to the one function that needs it, so you define it inside that function's scope instead. The second thing you gain is control over the flow of control. Look again at the two-line version. Once doubler holds the returned function, nothing forces you to call it on the very next line. You can put a dozen other lines in between, read a file, ask the user a question, run a loop, and only then call doubler of 3. You have deliberately interrupted the flow of control. You grabbed the function back out of makeprod, held it, did other work, and finished the computation at a moment of your choosing. The chained form gives you no such gap. Makeprod returns and the second call happens immediately. The third thing is the broadest. For trivial doubling, it hardly matters, but in a large program, functions, returning functions are another tool for decomposition and abstraction. The same habit that pushes you toward organized, robust, readable code. You do not have to write programs this way, you do have to be able to read code that does. When you see a name assigned from a function call and then called itself, you now know what happened. The inner function was built inside a private scope, handed out as a plain value, given a second name, and run later with its captured surroundings still intact. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.